Hello again, this is Mr. B. Hill. Today we're going to be talking about two things. The first one is going to be about factoring completely, which we've kind of already done in class some. And the second thing is going to be applying the zero product property to solve polynomial equations, which again we've also kind of talked about in class, but we're just going to do a quick little few examples here. So for factoring completely, got to do three things. The first one is to factor out any greatest common factor in each of the terms of the polynomial if it's a bit different from 1. Always a good idea to always factor out the GCF first. Next, whatever's left after factor out the GCF, factor the resulting polynomial. I'll look at an example to show you that. And finally, make sure that all factors are factored. So let's do a quick example here. Call it example 1. And let's say here maybe 7x cubed minus 343x. So first thing we want to do is factor out a GCF. Clearly both terms have a factor of x in them. This one has a factor of 7, but so does 343 have a factor of 7 in it? Let's check. Divide that by 7 and, oh, yep, 49. Great. So what we need to do is factor that common factor of 7x out of both of these terms. So when we do that, 7x will be brought out to the front. What's left over here, we pulled the 7 out, we pulled one of these x's out, so we've got x squared left, minus, we pulled a factor of 7 out of this 343 and this factor of x, so what's left over was, wouldn't you know it, that 49 right there. Okay, so we've factored the GCF out of these two terms. Now the resulting polynomial is this guy right here, the x squared minus 49. So if we can, we need to factor that as well. And wouldn't you know it, 49 happens to be a perfect square. So this is going to be 7x times x plus the square root of 49, which is 7, and x minus that square root of 49, which is also 7. Then we just want to make sure that each factor is factored. So 7, well, that's prime, that's good, no problem, x. And these two are both linear factors, as is the x. And linear factors are always factored. You can't factor them anymore. They're what we call irreducible in polynomial terms. It's the same thing as prime for numbers. Okay, so let's do another example. We'll call this one example 2. Maybe let's try 4x to the 4th minus 64. So first off, we need to identify the GCF, the greatest common factor between these two terms. And this one has no x's in it, so no problem there. But a factor of 4, of course 64 does have a factor of 4 in it. So we'll factor that GCF of 4 out. And what we're left with is the x to the 4th in the first term minus, now we've pulled out a factor of 64, and 64 is actually 4 times 16. So we have, that is the resulting polynomial, x to the 4th minus 16. Okay. So now we need to factor this thing if we can. Now notice we got a difference here. 16 is a perfect square, and actually x to the 4th is also a perfect square, because x squared squared is x to the 4th. So this is really a difference of squares here. So that'll factor as x squared plus 4 times x squared minus 4. And so now we've factored the resulting polynomial, but let's make sure that each of these factors are factored. Well, it turns out that this guy right here is also the difference of squares, so we can factor this down more. So this is actually going to be equal to 4 times x squared plus 4 times, well, the square root of this, x, plus the square root of this, 2, times square root of this minus the square root of this. So x squared minus 4 factors as x plus 2 times x minus 2. So now we have 4 factors here, the 4, the x squared plus 4, x plus 2, and x minus 2. These are linear, so they cannot be factored anymore. This guy right here, though, the x squared plus 4, that's a quadratic. So we might try to factor that some more. But no matter how hard you try, you aren't going to be able to do that. So what I'm going to do here is, notice this is the sum of two perfect squares, x squared and 4. So a bonus problem that I'm going to leave for you guys, we'll call this bonus problem 5 to go along with the other 4 that are up on the website. And the basic question is, why can't you factor the sum of two squares? Okay. Clearly we see that we've already covered this. The difference of two squares, that factors, but the sum of two squares does not. So write up a little explanation for why that can't happen, and that'll be worth some bonus points. And that's basically factoring completely. Now, the zero product property is how we're going to use factoring to solve polynomial equations. And we've talked about this in class before again. The zero product property basically says that if you have a product of two things, say A and B, and that product equals 0, then one of those two things has to be 0. And we've talked about why this is. Basically, a positive times a positive is a positive, a negative times a negative is also a positive, and a positive times a negative is a negative. We didn't get an answer of 0 for any of those situations. The only other possibility is we have one of these two things in the product being neither positive nor negative, meaning 0. So how we're going to use this, a quick example here, we'll call this example 1 for our zero product property. If we have, say, x squared minus 5x plus 6 equals 0, well, we can look at this and see if we can factor it. Well, yes, we can. 2 times 3 is 6, but 2 plus 3 is 5, but notice we wanted a negative 5, so how about we use negative 2 and negative 3? So basically, this thing is going to factor down as x plus negative 2 or x minus 2 times x plus negative 3 or x minus 3 equals 0. So the product of these two things equals 0, which means one of those two things has to be 0. So either x minus 2 equals 0 or x minus 3 equals 0. And those are two easy little linear equations to solve. Of course, we could add 2 to both sides here, getting x equals 2, or x minus 3 equals 0. Of course, that means that x has to equal 3. So our solution set for the equation is going to be 2 and 3. And of course, we can check these by plugging them back into the original equation, seeing if we get a true statement out. So let's do something a little bit more difficult here for one more extra example. We'll call this example 2. And we're going to even go more than a quadratic. Let's do a cubic. 3x cubed is equal to 27x. Now, if we're going to solve this by factoring, of course, we need to have the product equaling 0, meaning we need to have a 0 on one side. Easy way to do that is just subtract 27x from both sides. So this equation would be equivalent to 3x cubed minus 27x is equal to 0. Now we just want to factor this polynomial expression completely. The GCF here between these two terms is of course going to involve 3, because 3 is a factor of 27, and well, we also have a factor of x. So this is going to be 3x times, well, what's left over? We pulled a factor of x and a factor of 3, so what's left is x squared, minus, we pulled the x out, and we pulled a factor of 3 out, so what's left there is just 9. And that is all supposed to equal 0. So we pulled out the GCF. Now we need to see if we can factor this guy. X squared minus 9. Well, 9 is a perfect square, so yeah, this is going to factor as, well, we still have our 3x, and then we have x plus 3 times x minus 3, and that's now supposed to equal 0. So now what we have is a product of four things, 3 times x plus 3 times x minus 3. And the product of those four things has to equal 0. So either 3 equals 0, or x equals 0, or x plus 3 equals 0, or x minus 3 equals 0. Well, obviously 3 cannot equal 0, so we just throw that one right out. X equals 0 here, okay, so that's one possibility. Or here, if x plus 3 equals 0, then clearly x has to equal negative 3. Now if x minus 3 equals 0, that means that x has to equal positive 3. So now our solution set S is going to consist of the numbers 0, negative 3, and positive 3. And of course we can't check those by plugging them back into the original equation and seeing if we get a true statement out of it. I'll leave that for you guys to do. And so with that, I'm just going to leave you with some practice problems. Solve each of those by factoring completely and then applying the zero product property. Have fun with them.